Okay, everyone, let's get started. So it's 10:02. There are 31 people here, and I am looking through the list of participants, and I'm very happy to see that basically everyone's name is familiar to me. So all of you are doing the right thing. You're all showing up. You're all, I think most of you are submitting your homework. So thanks for being here. This is going to be a really fun week, and it's going to be something that really sticks with you for a long time. So I know I keep saying that kind of about every topic, but this topic is truly fundamental to nature. It's fundamental to economics. It's fundamental to medicine. So yeah, there is something in this for everyone. So first, I just wanted to start by asking if anyone has any questions about sort of general questions, about the course, about, let's see, okay, I'm on the chat now. So if anyone has any questions about just the direction of the course, you can ask now. If you have any questions, if anyone has started the homework. I assume people haven't started the homework, so being a Monday. But I did want to give some feedback on the last homework. Okay, so I was looking at the grades, and some of the grades are going up and some of the grades are going down. So some people are doing better and some people are doing worse. And it's, again, totally fine to not do well on the homework because you're allowed to do corrections. So keep in mind that the scholarship requires a B minus at the least, okay, in this course. And so if you really want the scholarship, and I think that most of you do, you can submit corrections anytime between now and the end of the course, okay, to your tutor. I did want to summarize sort of the what we've talked about so far in the course and where we're headed. So the first thing we talked about, what was the very first thing? Someone tell me.
Linear functions.
Linear equations. And then we talked about inequalities and absolute value. And then what did we talk about? Sort of seeing how much of this has stuck.
Absolute.
I forgot the third one. The fourth one's quadratic.
We talked a bit about dimensional analysis.
Oh, yeah.
Right? And this was sort of a thing that didn't fit exactly in the progression of things that we were doing, because these are all very graphical topics, right? Very algebraic things. This is algebraic, but it's sort of more of a science thing. It was really a topic that I was looking to put somewhere else, but it didn't really fit in anywhere. But it's not a terribly conceptually challenging topic, so I decided to put it in early in the course. And then we last talked about, as someone said, quadratics. And so barring this third kind of thing here, you can see that we're going from simple to more sophisticated, right? So we talked about linear things and basically how simple it is to solve a linear equation, systems of linear equations. And then we slowly built our way up into finer cases and absolute value, and then we made it into quadratics. Now we're going to get into an area that is actually removed from this family of functions. So linear equations were of this form. Okay, I'm gonna write this form, and it's a very general thing that I'm about to write. Okay, so linear equations were of this form, right? And then quadratic equations, we talked about how we just increase the degree by 1 and add this arbitrary coefficient. These were quadratic equations. And at the end of the last lecture, we learned that this pattern can be continued to cubic equations. See the pattern? See ax plus b, x squared, so I added a degree. This got a factor of x, and then I had to add a thing that goes as x to the 0. Now I've done the same thing, x squared became x cubed, x became x squared. So you see the pattern, and then you could keep going. So cubic, someone tell me what this one is called. Quartic, very good. And it keeps going on and on. It's really just linguistics at that point, right? So quartic, then quintic, and so on and so forth. And we said last time, I did not prove, because that's actually very hard to prove, that there is no solution to a quintic and above polynomial. So quartic polynomials have solutions that can be expressed exactly, right? Just like we found the quadratic formula and x is minus b over m as the solution to this equation. So we didn't present a general solution for the cubic, and we didn't present a general solution for the quartic, but they exist. But it turns out that there's no higher type of this looking thing that has a general solution. And what are all of these called? What is this sort of progression? What do all of these belong in? Does anyone know? They all have a name. So this is linear, quadratic, cubic. But what are all of them described as? I'm sure you all have heard this word. No one. Okay, it starts with a P.
Parabolas.
They're not all parabolas, because this is a line. This is a parabola. This is not really a parabola. It kind of looks like this, right? Well, they're all called polynomials, okay? And polynomials constitute a vast sort of part of math, okay? They're very beautiful, right? Because they're very simple to find, right? The form is very simple. They can be studied very well, especially these first few. They have general solutions, these first four. And you'll learn, for the seniors, you'll learn in calculus. At the end of maybe if you're taking BC calculus, you'll learn at the very end of your course that any function, literally anything, doesn't have to be a polynomial. It can be, sine, cosine, whatever. It can be an exponential function. It can be anything. You can express anything as the sum of polynomials. And for the seniors, you'll learn that this is called a Taylor series. And this is very profound, okay? And it's sort of the basis of all of college math. And so it's worth studying sort of just the nature of these polynomials. But now we are going to talk about something very different from this. So what I'm saying is that for the seniors, you'll see one day that polynomials and trigonometric functions and exponential functions and all the different functions you learn, logarithmic functions, they're all actually related through calculus. But for the sake of this course, we're not talking about calculus here, these things are going to look like very different things. So polynomials are going to look very different from exponentials, which is going to look very different from logarithms, which is going to look very different from trigonometric functions. So all of these things are intimately related through calculus. But so I just want you to know that. But what we're going to talk about today, what we're going to start talking about, is something that is on the surface very different from polynomials. Okay, and that thing is the exponent. And the branch of functions describing the exponent, in other words, the analog to polynomials, it's just called exponential functions. But we're not going to really start by talking about exponential functions. I want to start by talking about exponents. And I'm going to use numbers, right? So we're gonna take powers of numbers and find some properties of exponents before we venture into this world of sort of functions and what makes a function and graphing and stuff. So that's sort of where we're headed, okay? Exponents and graphing, and then later in the week we're going to introduce logarithms, and your homework will cover just these two topics, exponents and logarithms. So does anyone have any questions about where we're going? When I say the word exponent, is it familiar to people? I wish there was like a way to do a survey like quickly, but is the word exponent not familiar to anyone? Don't be shy.
Can I say what it is?
Please say what it is. That's exactly what I was about to ask.
It's a number on top of the number. It's like the power 2. So it's like 2 times 2 instead of saying 2 times 2, you say 2 to the power 2.
Very good. So you gave us this case, and you said that this is the same thing as that. And so this is called the exponent. Is that what you're saying?
Yeah.
Okay, great. So what if I had, hey, look, this was my first example. So what is 2 times 2?
5.
Uh-oh. Okay. Hold on. Was that who I thought it was?
I was just kidding. It's 4.
I would have been very alarmed. This was actually the first, I remember when I was very young, I have an older brother, and my older brother and his friend were testing me. They wanted to see how much math I knew. And I didn't know much back then. I was like 4 or 5 years old. And they asked me what 2 squared was. And this is the only square I knew at that age, because I didn't really know what the square was. And I knew that this was 2 times 2, and that's 4. But I didn't, if you had told me what 2 cubed is, I wouldn't have been able to tell you. So anyway, I have a personal affiliation with this. And this is the only square of a number that equals, it just happens to equal the base times the exponent. But that's obviously not generally true. A to the b does not generally equal a times b. And this is a mistake that I think the 9th and 10th graders will find themselves making a lot. This is absolutely not true. The exponent, to be formal, is the number of times you multiply the base by itself. So I'll say that again. The exponent is the number of times you multiply the base by itself. So if I have 2 cubed, well, the exponent is 3. So 3 is the number of times I multiply the base by itself. So here's the base. I'm going to multiply it by itself 3 times. And that's 8, for example. So that's the definition of the exponent. Okay. Speaking of which, what is 2 cubed?
8.
Very good. How about 2 to the 4th?
16.
Yes, and how are we doing this? Because for the people who are new to exponents, I'll write it out. 4 is the number of times we multiply the base by itself. So 1, 2, 3, 4. And 2 times 2 is 4. This 2 times 2 is 4. And so 4 times 4 is 16. Very good. How about 2 to the 5th?
32.
Yes. And how is I'm guessing this is Adi, how are you finding that so quickly?
You just multiply the last number by 2. So it's
Yeah. So in this example, you can see that this exponent is being raised by 1 every time. So Adi is just taking this, multiplying it by 2, taking that, multiplying it by 2, taking that, multiplying it by 2. So he's recognized the pattern in my example. But if you didn't know what 2 to the 5th was, you would just do 2 times 2 times 2 times 2 times 2. And you would do this just, kind of brute force. So 2 times 2 is 4. This is 4. So that's 16 times 2. 16 times 2 is 32. And 2 to the 6th. What is that?
64.
60 what?
4.
64. And if you didn't know, you could write it out, so on and so forth. Is this familiar? I mean, do people feel comfortable with this? I want to make sure I'm not leaving anyone behind here, especially 9th and 10th graders. This might be new to some people. Let's see, chat. Where is the chat? Okay. Yes, so some people are saying yes. If this is not familiar to you, please go to the office hours. I can only take so much time explaining this basic stuff, okay? Now, what happens if your exponent is negative?
It's a fraction.
Very good. So it's exactly what it is. So Alexis said in the chat, Alexis gave me the first one, and he said that 2 to the negative 2 is 1/2 squared, which is 1/4. So generally, if you have a negative exponent, I'll say a to the negative b. Actually, let's not be as general, and just for the sake of making people comfortable. What if I had a to the negative 1? Well, by definition, and this is written on your homework if you forget, by definition, a to the negative 1 is 1 over a. And a to the negative 2 is 1 over a squared, so on and so forth. So all the negative sign does is it puts everything in the denominator. So basically, you see the way I've written this? These things are the same, except they're off by basically
Fraction, basically.
they're not, I shouldn't even say that. Basically, this column, it's identical to this column, but this is the reciprocal. This entire column is the reciprocal of this column. So let's just do it explicitly. So 2 to the negative 2, as Alexis said, is 1 over 2 squared, right? Because of this negative sign. See, I've applied the definition. In fact, this is exactly this case, right? And then 2 squared is 4, so this is 1/4 or 0.25. See, people are writing in the chat. Yep. Okay, 2 to the negative 3. Well, that's the same thing as 2 to the 3rd, but it's in the denominator now. And what is that? Well, we don't even have to do it because it's written here. And you can go so on and so forth, right? So what is this? Someone, anyone?
No, that's 160.
Yep. I'm literally just taking the reciprocal of this side, so I won't even ask people. This is pretty obvious. Okay, so this is what the negative exponent does. It makes you, you have to put a 1, and so as soon as you see a negative exponent, I would do this step. So if you generally see a to the negative b, I would just write that, especially on the SAT, because it's easier for most people to work with fractions than it is to work with negative exponents, at least when you start out, okay? We're going to talk a lot more about exponent rules, okay, in just a few minutes. So, but this is the general rule, okay? Lots of this is about sort of being able to convert between exponents and fractions and radicals and so on and so forth. So can someone tell me what 2 to the power of 1 is? By the definition of the exponent.
2.
It's 2, and does that make sense with the definition of the exponent? The exponent says that this is the number of times I multiply 2 by itself. So if I take 2 and I only have to multiply it by itself once, well then I don't, it's just 2, right? Because this is linguistically hard for me to say, because when I say you multiply by itself,
The exponent determines the amount of times the number is like stated. So like if it's 2 to the power of 2, it's 2 times 2. Here it's only 1, so you only write it once.
That was a much better explanation than what I just said. So I hope everyone heard that. Thanks, Adi. That was very nice. I'll start using your language. How about this?
1.
1. And this is the hard one for people, right? Because it's like, some people want to say 0. But Adi, can you rationalize, according to your definition, why 2 to the 0 is 1?
Anything to the 0th power is 1. I don't know how to explain that.
Yeah, it's hard to use words to explain this fact. The easiest way to explain this is to look at powers of any number. I think the powers of 10 are easy to look at. So if you had 10 squared, 10 to the 1st, 10 to the 0, 10 to the negative 1, 10 to the negative 2, you can see that there's like the symmetry here, right? So 2, 1, 0, negative 1, 2. And you know that this is 100 and that this is 10. And I'll leave this blank for now. But you know that this, by the definition of the negative exponent, is 1/10, and this is 1/100th, right? And you can see, and I can write this as 0.1 and 0.01. And you can see that if we were to follow the pattern here, the number of zeros is decreasing by 1 each time. And here, the number of zeros, gets flipped to the other side of the decimal, so to speak. And there's always a 1 here, right? So sort of following the pattern, this is 1. That's the best explanation I can give.
You can think of it as in like the exponents. Like if there's a 0, then there's just the number, and then 10 to the power of 1. That means there's 1 0, and then 10 to the power of 2 means there's 2 zeros after the 1, and so on.
It's hard to actually explain 0 because it's like one of those things you just can't really do much about.
Yeah, I guess it's more definitional, but it's
more if you know it, you don't.
Yeah, so I would tell people to memorize that, any exponent to the 0th power is 1. Sorry, anything to the 0th power is 1. I hope one. So Adi contributed. I don't know who was it who also said something. That was very helpful. Someone else contributed, and this was my explanation. So between those 3 things, I hope this statement makes sense. How about 2 to the negative 1?
1/2.
1/2. Yeah. So these are sort of the special cases. They're not special cases, but they're almost like identities, right? You should know these off the top of your head. And this applies to anything. So I could change this number to 10. We show that 10 to the 1 is 10, 10 to the 0 is 1, 10 to the negative 1 is. So in other words, you can change the base, right? So if I had e, like some transcendental number e, e to the 1 is e to the 0 is 1, and e to the negative 1 is 1 over e, so on and so forth. So people see this pattern? Okay. So exponents, in summary of this entire discussion, exponents are just an efficient way of presenting very large numbers and also very small numbers. So instead of writing like a bunch of zeros and a big decimal, you can very efficiently capture that information just in this superscript here, right? So it's in a sense, exponents don't follow this notation does not follow our old sort of understanding of algebra. Like I'll give you an example. So say I had this algebra problem and I asked you to solve for x, what would you say? Or
X is 10.
Here's an even better, let's see. Yeah, okay, let's use this. X is 10, right? This is just an example. What if I had this? Does this follow, like, can you divide by this? Like, how do you solve this kind of thing?
You convert it to a log.
Yeah, so it turns out that you can't just divide. You can't divide by a superscript. You can't do this kind of thing. So what I'm getting at is that unlike multiplication and addition and subtraction, these exponents have their own rules because they're written in a way that is actually a bunch of multiplication. Because what is x to the 10th? That's x times x times x, 10 times. So you can't just divide by like the superscript. You can't just so what I'm getting at is that, yeah, so these are called transcendental functions, like exponents, logs, sine, cosine, all those things are called transcendental because they transcend the old middle school understanding of algebra where you would divide. One of my calculus teachers in high school always gave me this example. And some of you might not understand what this means, but say I had this kind of statement, right? And students would always come up to, this is a transcendental function, and students would always, coming out of 10th grade or whatever, or 11th grade, they would say, oh, you can just divide by sine. Well, no, you can't, because sine is not like a number. Sine is a function. And similarly, to raise something to a power, it's sort of a function. It's not just a number. There's more in here than just a multiplicative relationship or an additive.
I mean, you can do that if you're dealing with other functions.
You can do that if you're dealing.
You can divide by sine if it's like, not just sine, sorry, like if you do sine x.
Sure. So yeah, if you divide by, but then you're left with the same problem. Well, and this is
exactly
what we're talking about. But yeah, you can't just divide by the name of a function, is what I'm saying. Okay. That was more roundabout than it needed to be. But these are called transcendental functions because they're an efficient way of presenting large and small numbers. Let's see, people are messing in the chat. I have to keep an eye on this. People are saying 10. Anyway, so we talked about the powers of 10 already, and you'd watched that video, 2 weeks ago now, I guess, called The Powers of 10. And you took that little quiz on it, and you saw just the in I think the top left corner, as they would zoom out and they would zoom in, they would give you 10, and then they'd give you the exponent. And that's a much more efficient way than writing like 10 and then the number of zeros that exponent carries. So you've seen that video, you've been familiar with this, and in fact, the first homework assignment had a bit about exponents, and you have already seen some of these rules. But I want to sort of develop some more intuition about this idea of exponents, and I also want to just very briefly, in 5 minutes, talk about this idea of scientific notation, because this is on the SAT. And it's related to exponents. No, sorry, I can't write.
Wait, did you say it's on the SAT or not?
It is. From what I understand, the scientific notation is tested on the SAT. So this is a typical question that they would give. Like express
Oh, yeah.
300, first of all, this number is 300 million meters per second conveniently. So how would I write this in like scientific notation? Or in other words, how would I write this conveniently?
3.0 times 10 to the 7th? Or just 3 times 10 to the 8th?
Count the number of zeros. There are 8 zeros.
So 3 times 10 to the 8th, probably.
Yeah, and we'll ditch this 0.0. I think I know where you're coming from. But yes, 3 times 10 to the 8th would be this number in scientific notation. So all of this information got captured in this times 10 to the 8th, and this is right there. Okay, so this is a classic example. So the way you would write something in scientific notation is you write basically the first number as a number between 1 and 10. So if that first number is x, you would write that as just by itself, and then you multiply it by 10 to the whatever power is necessary to capture the magnitude of this number. So let's do a few examples. It's easier to do than to say. But by the way, does anyone know what this number is? Meters per second.
Meters over second, like to calculate speed.
What is that?
You use it to calculate speed of light or whatever.
Yeah, it's actually the speed of light, which is beyond the scope. Very good, Matthew. Yeah. So people, okay. Anyway, this is the speed of light, and it's a really beautiful result. Okay, let's convert this number. So someone besides Adi, because I think Adi understands how to do this. Let's see, Daniela. I'm going to call on people. Daniela, can you help me convert this to scientific notation?
It's going to be 6.022, times 10 to the power of...
It's okay. I'll tell you the number of zeros. They're 23.
Okay.
So 10 to the what?
26.
26?
Isn't it? Like the zeros after the 2?
Oh, no, you're absolutely, sorry. They're not, sorry. You are absolutely, okay. I should have counted the number of zeros because when I wrote this problem, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There are 20 zeros. So what's this going to be?
23.
20, yeah, 23. Very good. So sorry, I told you the wrong number of zeros. Okay, so she did it very well. And the way she did it was she looked for she went, down from the side of the number, and she picked a number that's between 1 and 10, right? So that's basically 6.022. That's a number between 1 and 10. And so that's the number that gets thrown out here. And then everything else, all of this stuff, the size of it is captured by this times 10 to the 23rd. So there are 20 zeros, right? And then you will also have these 3 decimals. And that's where the 23 came from. So I don't know if I'm doing a good job explaining this, because to me, this is so intuitive, and I've done this for so long that I'm probably not explaining this well. But does anyone know what this number is? Anyone who's taking chemistry or something? Yeah, so some people, yeah, it's Avogadro's number, which is anyway, we don't need to talk about it. Okay, let's do this one. Someone else, let's see. Maria. I'm not sure if Maria is there. Monty. Okay, honestly, anyone, just go for it. Okay, so yes. So the answer is in the chat. Anyway, yeah, so you look at this number, you look for a number. Let's see how you did this. Yeah, so actually 13.8, whoever put that, 13.8 is not, not scientific notation. Go ahead.
Isn't it 1.38 to the power of times 10 to the power of 10?
That's correct. Yeah, that would be the correct scientific notation thing. So 13.8, this is actually wrong. This is not in scientific notation. And the SAT people will get you between this distinction. Why is this not in scientific notation, even though it's equal to this?
Because it's not less than 10.
Yeah, that number has to be between 1 and 10. So this is the would be the right answer. But honestly, this is probably the way it's more frequently described, because 10 to the 9th is a billion. 10 to the 10th is 10 billion. So it doesn't roll off the tongue as well. This is 13.8 billion. This is 1.38 10 billion. You're not going to hear people say 1.38 10 billion. You're going to hear people say 13.8 billion. And so I think people are comfortable with this. People are complaining about significant. You don't have to know about significant figures. That I am not a fan of significant figures. It is such, that needs to be phased out of public education because no one actually, okay, anyway, that's my own rant. Does anyone know what this number is, what it means? It's okay if you, I mean, it's the age of the universe, which is a pretty cool number, okay? But it's the age of the universe. And we talked about how that was found, using the Hubble. It's 1 over the Hubble constant. Anyway, that's beyond what we need. So anyway, yeah, you get the scope, you get sort of the main idea here. In scientific notation, this is 1.38 times 10 to the 10. Okay, now let's transition to talking about a more symbolic discussion. And for that, we're going to use the number pi. Okay, so so far we've been using numbers like digits, I want to use pi because, it's still a number, but it's a symbol. And from that, we're going to transition truly to variables, okay? And then the true reward of this discussion will come out. We will talk about, so Aditya, is that the same as Adi or no? Is that two different people? Sorry if, okay, it's two different people, okay. Okay, so we have Adi and we have Aditya, okay. Yes, we're gonna talk about Euler's number a bit today and a bit tomorrow. Okay, so what is pi squared? What is this equal to? Well, it's just, according to the definition of exponent, this is just pi times pi. And you could multiply this out and write it as a number, but this is actually the most efficient way to write pi squared. If you ever come out with a result that's pi times pi, you would write it as pi squared. So what would pi squared times pi equal? Well, go ahead.
Pi cubed.
Very good. And the way you found that was that, look, I'm going to write pi squared as pi times pi. So this is pi times pi. And then I have this extra pi. And look, this is just pi multiplied by itself 3 times. And by the definition of exponents, that's just pi cubed. Okay? How about this?
Just pi.
It's just pi, and the way I know that by, again, I can write pi squared as pi times pi. And now I have this divided by pi. And generally, when you have a number, the same number in the denominator and the numerator, and everything's in a multiplicative relationship, you can cancel common factors. And so there is this pi and pi exists, and you're left with just pi. So very good. So these are 3 sort of results, right? You have, well, this isn't really a result, this is just definition, but generally you have, okay, when the base is the same, see the base, that's what this pi is. When the base is the same, you can add the exponents. So look, there's a 1 up here, right? Pi is just pi to the 1. And the result is just the base to the power of the sum of these exponents. See, 2 plus 1 is 3. And similarly, here, look, the exponent is 1. And I could have also written this as pi squared times pi to the negative 1, right? That's what we talked about, that the negative exponent is just a fraction. And here, the base is the same. And I'm actually doing the same thing. I'm adding the exponents. And here, 2 plus minus 1 is 2 minus 1. And 2 minus 1 is 1. And pi to the 1 is 1. Pi to the 1 is pi, sorry. So clearly, when the base is the same, you can add the exponents. That's sort of the big takeaway. How about this one? Pi squared all cubed. Well,
To the 6th.
yeah, it's pi. And so how do you know? Well, I'm going to write it out for people who have not seen this before. Pi squared is this, right? you agree that this is the same. I just rewrote pi squared as pi times pi. Now the cube means that I take all of this and I multiply it by itself 3 times. So here's number 1. This is the second time, and here's the third time. So everyone see how I got from here to here? I'm just following the definition of the exponent. And pi, how many pi's? I mean, now we can use sort of what you know as the associative property of multiplication, which means that none of these, all these things are in a multiplicative relationship. So none of these parentheses matter. Go ahead.
I have a question.
Go ahead.
So, can you apply the 3 to the 2? Like 2 times 3 is.
That's exactly what we're going to find. I'm not proving that result to you, but I'm showing that it's true with pi. Okay. So just hang on just 1 second, and I'll say that formally. So here you have pi multiplied by itself 6 times, and that's pi to the 6th. So yeah, you're exactly right. Apparently, when you have some number a, and then raised to the power m, and then that's all raised to the power n, this is just a to the power m times n. And I'm sort of taking this this is not a proof, okay? This is, using an example and sort of generalizing. But this is true, okay? And this is very powerful, and you'll need this for the homework. So in this case, indeed, pi squared cubed is just pi to the 6th. And I did that the long way, but if you want to do it the short way, the way you should do it is you do 2 times 3, which is 6. So we've shown sort of that these things are true for these numbers, because pi is actually a number, but I used it because it's actually a nice symbol, okay? And it can be thought of almost as a variable. It's not a variable, but it looks like, it behaves like a variable. So these are the properties generalizing the 3 results we found above. And so this is actually written on your homework. So if you forget to write this down now, or if you need a reminder on the homework, it's all there.
Is this just a minus b?
A minus.
Or like, does it say b, or is it?
Oh, so sorry. Okay, so I should have said I've used Greek letters here. I should not.
The backwards R is a Greek letter.
It's not okay. So I should not have used Greek letters. This is something people do in college a lot. I should not have done that. Sorry. Okay. The short aside is that the Greek alphabet, the first 3 letters of the Greek alphabet are alpha, beta, and gamma. Okay, just how we have A, B, and C. So you can see the semblance. So just don't think of them as anything different. You could rewrite, if you don't like the Greek letters, I don't care. You can write this as in terms of A, B, and C. Does that make sense? Just think of them as symbols. Don't think of them as anything different. Sorry, I should have used English, the English lexicon. But that's a good question. Yeah, it is a good question. Say that again. Okay, must have been some background noise. Honestly, I would suggest people memorize if you want if you're looking for a career and if you're thinking about pursuing like math, physics, any of those things, or engineering, I'd go through the Greek alphabet and just like Wikipedia, and just sort of start memorizing. Because it's first of all, it's impressive superficially, and it's just good to know. Okay, so yeah, alpha, beta, and this is gamma. So these are the properties we found, and now let's just do a few examples that are similar to the ones on the homework, where you use these properties. So a to the 4th divided by a. Well, which property am I going to use? 1, 2, or 3?
1.
Okay, we can try. I mean, that's maybe the first step. And so from property 1,
Do you have to use a property? It's just kind of easy division.
Well, all of these problems require, you don't have to tell me which property you're using on the homework, but you are using these properties whether you know it or not, so to speak. So I'm just trying to show people, I mean, how to employ this information. So from property 1, I would write this a in the denominator as a to the negative 1. And now what do I do?
You subtract the exponents.
And which property is that?
That's the second property.
Yep.
The second one.
And so that's a to the what?
Third.
Yep, that's exactly right. And so eventually, I think most people will get past this intermediate step of using property 1, and they'll just see this, and they'll say, oh, that's just a to the third. They'll sort of do this in their head. This will become very intuitive, and I have a feeling it's very intuitive to most people already. Okay, so let's kind of go fast through this. Let's see, I'm going to call on someone else. Someone I haven't heard from. Is it Tiobsta? I feel like I'm mispronouncing your name. Is that how you pronounce your name?
It's Tiobsta.
Tiobsta. Is that right?
Yeah.
Okay. Thanks. Sorry for mispronouncing your name. Okay, can you tell me what this is?
Would it be b to the power of 100 times b to the power of negative 10?
Very good. And so you use property 1 for that. And I'll go up here. This is property 1. Just the fact that the negative exponent is 1 over the exponent. And now what do I do?
And that would just be, you can add 100 and negative 10, and that would be b to the power of 90.
Very good. Yeah, so you just use property 2 and then, yep. And so again, you know, this middle step, thanks for mentioning it, but yeah, I would expect that people can, you know, kind of surpass that stage, okay? But this is formally what we're doing, okay? Let's see, I'm gonna call on someone else. Let's see, Brianna. Brianna is not there. Biruk. Brianna is there. Okay.
Did you call me or someone else?
I don't know who's talking, honestly. I can't see. But go ahead, whoever it is.
Leanne.
Okay, great. Yeah, what is this? Which property should I use? I'm sort of scrolling back and forth. How should I do this?
Can you go up again?
Yep. All right. Oh, sorry. Moving things around here.
Property 2.
Yep, property 2. And let's put it out here. Yeah, and so what should it be?
A to the 9th.
Very good. Yay. So this is actually as simple as addition, right? In first and second grade, you people all learned 7 plus 2 is 9, 3 plus 3 is 6, so on and so forth. So really, this is just like addition for high schoolers, right? Okay, let's see. I'm gonna call this is slightly harder, but it's really not. It's really the same thing. Let's see, Isaac. Can you tell me what this is? Go ahead, Isaac. Just shout it out. Okay, okay, people are being shy. Mauricio?
It kind of looks like slope, but I don't think it is.
Isaac, you're gonna have to talk louder.
It looks like the slope formula, but I'm not sure. I'm not really sure.
Okay, you're not sure. Okay, so let's find someone to help. So here are the properties. Can anyone help Isaac? How would we go about this? First of all, I could write this as 2 independent fractions multiplied to each other.
I think it would be property 3.
It would be property 3, and property 3 takes an exponent and then it raises that entire thing to an exponent. And do we have that here? I don't think so, right? All the exponents are only raised once, right? We don't have something like this, right? We don't have a big, it's not all raised to an exponent. We don't have, so it's not property 3, but let's sort of walk you through this. So
is it property 1?
So by property 1, I could rewrite the denominator, this a cubed b to the 6. I could bring that to the numerator, so that's a good place to start. And when I do that, I have this. So this is property 1. Okay, now where? Now which property do I use?
Property 2.
Good. And now can you tell me the answer? So property 2 says that I add the exponents when I have the same base. So these have the same base. What's 8 minus 3?
8 minus 3 would be 5.
And what about the b's? See, I have b and b. So what's 4 minus 6?
-2.
Good. Exactly. Good job. How about this one? Anyone? Shout it out. We'll call on people.
We would use property 1 and 2 again.
You can use property 2, sure. And so from property 2, I would have this, right? Just bringing these terms to the numerator and putting a minus sign because we're doing that. And now I can add the exponents that share the common base. So the cube here and the -2 here, they share the j, and so 3 minus 2 is 1. 2 minus 1. Sorry, 2 minus 1 is 1. That's embarrassing. And then the y by itself. And so this just spells the word joy. Make sense? I assume so. Okay, what does it mean to raise something to a fractional exponent? So in all these examples, note that our exponents were numbers bigger than 1, or their magnitudes were bigger than 1. So they could be negative, but they weren't like numbers between -1 and 1, right? So what does it mean to raise something to a fractional exponent? What if I had this? What does that mean? It actually means it's another way to write the square root of something in this case. And so this might be familiar to some people, but by definition, a to the 1/2 is the square root of a. And a to the 1/3 is the cube root. And the way you write the cube root is you put a 3. This is called the index, I think it's called the index of the root. So whenever you see a fractional exponent, you can write that as a radical. So this bracket thing, I don't know what you want to call it. It's called a radical. And if that thing is a square, then it's just the radical by itself, square root. If that thing is any other number, then you put that number right here. Okay, so this is sort of definitional, and you'll get used to just going back and forth. And so what is 4 to the 1/2 by this definition?
-2.
It's not -2. By the definition, so here, I'll write the definition of a to the 1/2. That's just the square root of a. So from this definition, this should just be the square root of 4. And the square root of 4 is actually just +2. It's not -2. Okay? How about 100 to the 1/2? Well, that's just square root of 100 from this definition, and the square root of 100 is 10. How about this one? Someone tell me.
That's also 10.
Yep, and how'd you do it?
The cube root of 1000 is 10. It's just kind of those
So
properties.
as the cube root of 1000 from the definition, and it turns out that what this is saying is, what number, when multiplied by itself 3 times, is 1000, and that number is 10, because 10 times 10 times 10 is 1000. Okay, so that's the meaning of, here's one more example, maybe a few more examples. How about 27 to the 1/3? Well, you could write this
3.
as, ooh, that was a weird square. Yep, it's 3, and so this is the cubed root of 27. And this is asking you the question, what, when multiplied by itself 3 times, gives you the number 27? And 3 times 3 times 3 is 27. So the answer is 3. How about this one? Well, this is
2.
applying the definition. Yeah, so Audie's really kind of caught on. I'm just doing this for people who are not familiar with this yet, which is totally understandable. Use the definition. What multiplied itself 5 times by what multiplied gosh, I can't talk. What, when multiplied by itself 5 times, gives you the number 32? Well, it turns out that 2 times 2 times 2 times 2 times 2 is 32, and so the fifth root of 32 is 2. Sort of blazing through these. The main step is getting from here to here, right? Just applying the definition. What, when multiplied by itself 6 times, gives you the number 64? Well, that's actually 2. Okay. How about more generally, what is x squared to the 1/2? Which property would we apply?
The third one?
The third one, I'm going to find it.
I forgot.
Yep, it is the third one. And I'll move it down here. I should have interspersed this more when I was making this. Yep, so look, this looks a lot like property 3, right? Because you have an exponent raised to an exponent. And this property tells us that when you have that case, you just multiply the exponents. So here,
Just x.
2 times 1/2, x to the power of 2 times 1/2, and 2 times 1/2 is 1, right?
Yes.
This is just x to the 1, which is x. So I hope people are catching on. There's nothing really special about fractional exponents. They follow the same properties. They just, mathematically, they mean that you're taking either the square root or cube root, whatever that number is in the denominator of the exponent is the index of the radical. Okay. How about this one? Same idea. We apply property 3, and that tells
X squared.
Yep. So 6 times 1/3 is x squared. Because 6 times 1/3 is 2, so you're left with x squared. I hope this is making sense to people. We're almost done. Here's like a classic example of something you'd find on the homework, because I like to use words and see if you're catching on. So in this case, I'll sort of do this for you because you have several of these on the
You
homework.
just root all of the everything.
Sure. So you can.
It's just music.
Okay. Okay. So it might be easy to see because I've already used a word that this is going to spell out music, but let's show that that's true. You can either apply this 1/2 first, or you can simplify what's inside first. And because these are not all even numbers, because these things when multiplied by 1/2 will give you fractions, like in other words, not integers, I'm going to simplify this first, and then I'll deal with this later. So simplifying this, I can apply property 1, right, which says that a to the negative b is just 1 over a to the b. Well, I'm going to apply property 1 to the denominator, and this would give, so I'm writing the numerator m, so this right there, u to the 9th, u to the negative 7th, right? S to the 6th, s to the negative 4th, I cubed, I to the negative 1, c squared. And this is all raised to the 1/2 power. So this is from property 1. Where did that thing go? Copy this. Put it on here. Okay, so property 1 is what we've applied, okay? Now from property 2, I am going to simplify the rest, right? So all the things with the common base, their exponents just get added. And you're left with, m, 12 minus 10 is 2, 9 minus u, 9 minus 7 is 2, so on and so forth. All these things end up being 2, 2, 2. You see how cleverly I engineered this problem? And now which property do I use?
I think it's the third one.
Yep,
Yeah.
because look, I have exponents raised to another exponent. And this is really nice because all these exponents are 2, and 2 times 1/2 is 1. And so you're left with music. So in this is sort of the capstone example because we've used all 3 properties at once. When you see things like this, don't get scared, okay? This might be on the homework. I don't even remember at this point what's on the homework and what's not. But just, use your exponent properties, write this as x to the 1/2, all to the 1/2, right? And then multiply the exponent. So this is just x to the 1/4. So, and you could also write that as this. Sorry, I'm saying x, but it's a to the 1/4. That's the same thing as the 4th root of a. So these are just time. Yeah, so here, you could, when I look at this, I get scared, honestly. Like I start worrying, like, oh gosh, what? But the first thing I would do is I would write b to the, the cubed root of b, this inside part, that's just b to the 1/3, and then taking the cube root of that is raising everything to the 1/3, and that's just, using property 3.
Yeah.
Using property 3, that's b to the 1/9.
Yes.
1/3 times 1/3 is 1/9. Okay, so I'm going to stop there and send a quiz. Does anyone have any questions before the quiz? No questions, at least from Leanne. Okay, if you have questions, I'll stick around for the next few minutes. So the quiz is out. Yes, thank you, Matthew. The homework, yeah, you've also posted the homework link. I feel like it gets posted every day in this chat. The homework is due Friday, as always. Your homework grades will come back this week. The quadratic assignment grades will come back this week. So far, things are looking pretty good. Some people are not doing as well, but remember, you can do corrections. I've asked for some feedback, okay, in this quiz. That's the first question. It's required. So please write just a little bit. You don't have to answer all of those questions, but it would be nice just to get some feedback. And I'll stick around if people have any questions about anything.